Alright, so welcome back to our algorithms class. Today we will start talking about different graph and tree algorithms. We will start one of the most famous algorithms. Today we will look at the Dijkstra algorithm for single source shortest path problem. But of course we'll need to also define some terms, again for those who are not used to graph theory, and so some of the terminology, and also why would we want to study this? Maybe that's first, right? So in the simple terms, we have a collection of vertices. Let's say they could be cities or something on the routes or roads. We call them edges between them, right? And we want to find the from Riga all the shortest path to all the other cities, basically, right? So something you use in Google Maps, actually, or I don't know, Waze or anywhere where you want to find the shortest path. Actually, Dijkstra serves as the beginning for more improved algorithms, which actually are underneath the navigation system. But certainly, navigation is one of the ways where we use this shortest path problem. Also, network routing for computer networks, of course, as well. How to find the best way to send the packets from one source, through the multiple routers, right, bridges and so on, onto some destination. Also, of course, it could be also in supply chain logistics, right? You need to ship something, of course. Again, what's the best way to shipping things, right? Also, of course, it's used in where? What were these things used? In social network analysis, meaning you have some social networks, right? And you want to see how quickly you can get from one person to another person. Who do you need to meet to get to the president, basically, right? Or 6 Degrees of Kevin Bacon, those who have played the game of Kevin Bacon, the actor, right? How close are you to him, basically, right? So, also in finance, it's used in finance for risk analysis, but multiple use. But again, why is so? These uses stem from the fact that we can model these problems in terms of graphs. So maybe let's start with a sort of kind of formal definition of graphs, right? So what's a graph? Basically, I call it set, right, which includes edges and vertices, basically, right? So let me do some painting, right? Let's do some paint. You have not taken any formal graph theory. Anyone?
We will.
You will. Okay, good. So then we probably cover some of the stuff there also a little bit, right? So, right. So you have these are vertices, right? Right. And so we'll call them V, right? So I'll call it V and equals, right, to denote. And we'll call them A, B, C, D, or so on. Let's see. Can we have text here? I'm not good with my paint skills. Right. Oh, here we go. A. Right. So this will be A. Right. B. Right. And C. Of course, you can pick different names, right? So this is just a right. And of course, so this will be A, B, C, D. A, B, C, D. Right. And right. And I'll draw my funky. Right. So we define set of vertices, and then of course we have some connections, right? Let's make connections, right? So these we call edges. I should probably make a bigger, right? Bigger, fatter. Yeah, that's better. Be better color, right? And of course, they don't have to be all connected, right? How about A to E, right? Let's do this, right? Right. Of course, when I'm drawing, right, in formal terms, doesn't matter how you draw the lines, right? It's just connection, right? Well, in real life, it might matter, of course. So, in this particular case, we just have connections, right? And you could say, okay, E, right? So edges, right? And then you have to define them somehow, right? You could say AB. You say AB. That's one way of defining them, right? You could say, okay, AB. Then what? BC, BD, right? CE and EA, right? Okay, and now of course the question is, in this particular graph, we have not, doesn't matter whether I say BA or AB, right? That's the question. Does it matter or not?
No.
Not in this particular case, because, well, why? Because I don't have a direction defined, right? So this is so-called undirected graph, no direction, right? We have edges, we have vertices, right? And again, a very simple way of modeling many type of problems. So we could add direction, right? Then it starts to matter. Then suddenly this starts to matter. If I say, okay, if I put a little arrow here, right, this means that I cannot go from B to A, right? It starts to matter. Then this is absolutely necessary, right? AB, there's no BA here, right? And then of course again, I could do this to preserve everything, right? So that I don't retype this. Let's see, an EA, right? EA, right? And then maybe I want to do DA, right? Here, for example, right? Then I have to type it here, right? DA. I have to type it here, DA, DA, right? And so on. Right, I probably should type it Control Z. I should probably type it here, DA, right? Right, so then it matters. Then it is very important, right? That this is actually correct direction. And of course, in a directed graph, you can go backwards, right? You can go backwards, of course, that's completely fine. That's normal. You can do also this, right? So if I do this, right? So this is basically, this particular CE is basically just like undirected. It goes both ways, right? So you can always go from the undirected graph to directed because you just add arrows. You basically add, for each connection, basically you add 2 arrows back and forth, and you have a directed graph, right? So what works for directed graphs will work on undirected graphs because you can always make a transformation to the problem, right? So if you just have simple lines and you have this algorithm, this really cool algorithm which works on directed graphs, and you have undirected graph, no problem. You can convert it, right? You just add the arrows, basically duplicate all the edges and add arrows in each direction, but you add the direction. Okay. So I need to add to be completely while I'm talking. Hopefully, and hopefully I'm recording this, yes. So hopefully here I will have to also add comma EC, right? And then I'm done right here. Okay, and there's one more thing, of course, is that both vertices, right, and edges, what might they may have? What do you think? What they could have, right? Right now this is just a completely, let's say these are cities, right? Well, and let's say these are roads, for example. Right? And I guess these are one-way roads, right? There's no way back. It's like a one-way street or something. I don't know, right? From Riga to Čekava, I don't know. But so, what do they have? What's kind of missing? But maybe here I'm just like very minimal. But what's usually the case? What's going to be important? Length, yeah, length, some sort of property. Basically, it could be a road length. Could be what they call them weights, some sort of property or attribute, you could say, right? So usually the edges will have some weights. They could be 0 if you have a light speed travel, instant travel, for example, that's 0, right? Free cost. Also, could weights be negative?
No.
Well, why not? Who says I can be negative?
Well, can a road have a negative length?
Well, but think, okay, here's the deal. Okay, I'll tell you as a problem. Instead of road lengths, we have, these are cities, let's say these are still cities, right? But these are ticket costs, right? Go from one city to another. And for some reason, I don't know, Tukums is sponsoring travel from Riga, right? They want everybody to go. And they're offering actually money if you go there, right? So the ticket cost is negative. They are paying you to go there, right? So it is possible to have negative weights. I mean, again, it's possible to put, flying aliens there as well as property or something. I don't know, something silly. But in general, yes, it is possible to have negative weights. So, but this is, of course, all this big overview, right? So something to consider when you're dealing with some sort of problem, and it's presented as a graph problem. What kind of properties are there? Also, about the vertices. This is maybe less important, but in real life, of course, the vertices also have some properties, like Riga, population of Riga, some multiple properties, zillion properties of this vertex, right? Good morning. Good morning. Yeah. Now, so I'm explaining some basics of graph theory, again, you will probably cover some of it in graph theory class, right? And so we will see how we arrive at solution to this problem. So we are trying to find the shortest way to go from A to E, for example, right? And here you're smart. You say, okay, well, there's really not much choice here. It's obvious, right? It's only A, B, C, E, right? That's it. Of course. But what happens if I do one more thing? Let me add another pass here. Let me do this. Right? A direct direction, right? But now I'll add costs. Right? I'll do like, let's see, this is like, I don't know, 14. This is, I don't know, 5. This is like, I don't know, 3. This is going to be 2. And this is going to be, I don't know, 28. I don't know, right? Something like that. Or 25. Okay, and this is 5. And of course, here you have 3. And you have, I don't know, 4. Okay. And this will be maybe, I don't know, A. Okay, so now the question is, so from A to E, right? You have a direct connection of 25, right? But that's not the shortest path, because you have A, B, B, C, C, E. That's what? 14, 5, 3. That's going to be 22, right? 22, right? So that would be the answer here. Of course, this is extremely simple example. So, Dijkstra, again, we'll talk about his algorithm, basically came up with first like pretty decent algorithm. There are improvements to this algorithm, right? But hopefully by now you have this idea what we're trying to solve, right? We're trying to find the shortest path. So we want to find, of course, maybe you want to build a map from A, right? Alūksne, I don't know what city it would be, right? To Baldone, Daugavpils, I don't know, Cēsis, and A would be what city? Ērgļi, I don't know, maybe, yeah. So you want to find all the shortest paths. Okay. So that's kind of like a semi-formal definition of the problem, right? So now we go back to our Dijkstra, our friend. So Dijkstra is, or was actually, he was a very famous computer scientist who had strong opinions about many things, right? So he was sort of like, I wouldn't say he liked to annoy people, but he didn't really tolerate fools gladly. So he had lots of comments, and so he won Turing Award pretty early, actually. And he really hated Goto, right? Goto in programming, right? Wrote many influential essays, right? So he was one of the first like proponents of like structural programming, basically, right? He said, okay, don't do this, don't write spaghetti code, you know, don't jump around the code, basically. But also in like 1957, as the story goes, I think he was sitting in his cafe with his wife or a girlfriend, and basically like 10 minutes on a coffee, on a napkin, he wrote this algorithm, right? That's the story, right? And his paper was published like in late 50s for like 2-page paper, right? And he basically, he is probably best known for that algorithm, even though he was, I mean, among people who are not computer scientists, right? But otherwise, he had many other contributions, of course. He didn't get his Turing Award just for this algorithm, right? It'd be kind of nice, but, right, so I can't pronounce all his name completely fully, right? He was Dutch scientist, right? So not Edgar, but Edsger Vibe, I don't know. And Dijkstra, again, you can put this in a Google, you know, the tool which tries to pronounce it, right? So, okay, so let's go back to our problem. So something like this. So we have a vertex V, right? So one of these has to be a vertex, you know, which we are going to find. Later on, in the next lecture, or maybe the lecture after, we'll find the problem of finding all solutions, right? We'll look at also some improvements to Dijkstra. But for now, we have a single vertex where we start, and we want to find all the approach. So, how would we, if we had not read about any theory about this, how would we go about it, right? Well, again, first way would be, how do we do it? We could just do, what could we do?
Brute force search or
Yeah, brute force. So you just look at all solutions, find which one is shortest, right? You know, so the problem is, of course, that on a large graph, the number of solutions, I don't think it's even exponential. It might be at least exponential, at least, right? So, because even if you discount any previous, you know, duplicates, right? Because that's another question is, when you're looking at the problem, do you want to allow going back, right? You might say, okay, that's going to only increase the length, right? But what if you have this infinite money glitch, what I call it? If somebody's paying you to go somewhere, right? It might make sense to make a loop, right? Keep looping, and you just keep making money, right? That's going to complicate things. So Dijkstra assumes that the costs are positive, right? There's no sponsors, nothing like that, actually, right? You have to find the path, right? The shortest path actually is positive, so it keeps increasing. So this means that you don't want to go no loops, right? You don't want to loop anywhere, right? That's going to only make things worse. But yeah, still, let's say you go from 1, you want to find the shortest path to 6, right? And here, okay, in this case, if you don't see weights, what can you do? What can you do if you don't see any weights? Well, what would be the approach?
Well, you can assume that for all of the edges the weight is the same.
Yeah, so it could be 1 or 10 if you want, or 100, doesn't really matter, really, right? Just same unit weight. Usually you do 1. So again, that's not a showstopper. You have this algorithm which works for directed weighted graphs. You don't have direction, you don't have weights. No big deal. You can just put arrows both ways, right? You have add directions both ways, and also weights 1, and there you go, right? So again, one of the skills that you, when solving algorithmic problems, is to see if you can use some, you have a sort of novel problem, but maybe you can apply an algorithm from a different problem, right? So in this case, going back to our brute force, how would we find? So we basically, so 1, you got 2, but then you have 2 choices, right? So how many different ways can we go to 6? Let's see. Can we do it? So 1, 5, 4, 6, right? 1, 5, 2, 3, 4, 6. Okay, that's 2 ways. Okay, 1, 2, 5, 4, 6, and 1, 2, 3, 4. So only 4 ways, right? So brute force would basically be 4 ways, finding 4 different solutions. Okay, but now let's look at his solution. Right. In general case, this is not going to be, in a big graph, enumerating all solutions is going to be exponential. So we're going to use basically our old friend greedy approach, basically, right? So we have weighted graph, GEV, right, and source vertex, V, part of this, right, and all edge weights are non-negative, right? So what are we going to get out of it, right? We're going to get the length of the shortest path, right? Or possibly also we would want to see the actual road, right? Usually just the cost is not very interesting. You actually want to know what to do, right? I mean, that's also, right? Maybe academically, this is the shortest path, but of course you want to know the path, right? So we will see that this actually is also relatively easy to find, right? If you know the length, of course, you know the path. So so that's the algorithm. He came up with this algorithm again on a napkin, like in 10 minutes, right? So basic idea. We are going to assume we start somewhere, right? We're going to start somewhere. We start with 0, right? So we assume that we know if we are in Riga, the distance to Riga is 0, right? Kind of makes sense, right? Pretty normal assumption. Then make another reasonable assumption until we have explored our world, right? All our distances are infinity, right? Infinite distance, right? Also makes sense, right? You don't know anything about the rest of the world, right? You lived your life in Riga and never ventured outside. So and then you have a set of what you have visited, right? Your visitors, right? What you have seen, right? And basically you initialize to empty set. Right? Nothing. It's empty, right? So it could be some sort of collection. It could be a list or dictionary, something like that, doesn't matter. Or could it be actually a set, right? And then you set up a queue, right? Means you need to visit all the vertices, right? Right? So, because that's all you have, that's the work you have to do, right? You cannot finish until you have seen all the vertices, right? And then you do a while loop, while you still have work to do, while your queue, right? Some sort of structure, while there's some cities you have not visited, right? Now the tricky part is, right? You find the distance, right? which is the shortest, right? Minimum distance, right? And then you add it, right? So you check which your queue, right? It's all cities, right? And you find which one has the shortest distance to the distance the city you started with, you know, the original, the origin, the source, right? And if you think about it, right, in the beginning you have all the other cities are infinite, and the beginning city has a cost 0. So obviously this will find your original city, right? Because it's 0, right? It's a minimum, right? And you have it. You have your starting point, right? You don't have basically, so you don't have to initialize specifically. It's just gonna this part here, right, is gonna take care of this part, and then you add it. You say, okay, I know this is for sure. This is guaranteed. This is guaranteed distance. So I have visited the city. I know for sure this distance, and then what you do, you check neighbors of this city. So you go through the neighbors, and you see if you can find an improvement. And this is a tricky part here. We'll see this in graphics, right? So that you'll figure out this. This is kind of neat, right? So if you find a new path, right? And if it's a new path as improvement, you update the cost, right? So the beauty is that this means next time you do this loop, you will find the next shortest path. So the whole idea of this algorithm is that if you have some shortest path, right, you should always start with the one which is closest, right? Because why? Because this means you cannot improve on it, right? It's a safest choice. It's a greedy choice, right? You cannot improve on it, right? Because if you could improve, you would already know it. It's kind of like a slight paradox. Okay, let's take a look at example, right? Maybe again, and then in the second part of the course, we will actually make an algorithm, right? So look at this here, right? So this is the original queue, right? And we have 5 cities, A, B, C, D, right? And these are the costs. It's a directed graph. Look at these little arrows, right? You see the arrows, right? So we want to find the cost. So again, it's kind of obvious that from A to A is going to be 0. That's why it's initial, right? This part here, right? That's the part here, right? So on the set of what we have visited, we have not visited anything. So what we do is we go through with 3 I, B, C, D, E, and we find which one has the lowest cost, right? And that's going to be A, of course, obviously in the beginning, right? So we say, okay, we're going to mark it, right? We're going to mark, okay, this is like set in stone, right? So this moment here, right? We set A in stone. We are not going to have to go back to it, right? It's out of the queue, right? Queue it only has B, C, D, E, right? And we set 2 new costs, right? So 10 and 3. And here's the key point, right? At this moment, right, whichever of these has the lowest cost is already guaranteed, right? So A, B, and A, C, you think, okay, are we done with both of them? No, because you'll see there could be an improvement to one of them, right? But for the lowest one, which one is the lowest one? Obviously, C, right? Right? It's guaranteed. So what this means is we can go proceed. We find C. We take it out of the queue, right? And this is again, this cost, this 3 is set in stone, right? We can safely take C out. And now we're gonna update the neighbors, right? Again, we don't have direct connection back to A. We don't have to update it, but what are we going to do? We're going to check. We actually have connections to B, D, E, right? So let's take a look. So this is a crucial point. So these 3 arrows, right? So we had A, B was 10, but that was not guaranteed because this is not the closest one, right? So right now we're going through C. Again, the greedy approach, right? Always take the shortest one, right? Actually, best first, actually, right? So we need to update this because it was 10 and ACB, that's ACB, that's 7, that's better, right? So we need to update this 10, this is no good, right? So we need to update here, right? And then we had 11 here, right? Because we had infinity, so infinity, okay, so 11 and 5. Again, at the moment, we don't know which, you know, we're not completely sure yet of the rest of them. But which one are we gonna pick next? Which one? Yes, very good. Right, so actually, in fact, once we pick E, we know E is also solved. So we have solved A to C. So in fact, by the way, if you had a problem to solve only from Adaži to Carnikava, right, road, right, so A to C, right, we could quit here. We could have an early exit, right, if you only had a single, you know, between two destinations. We solved the problem, right, A and C. We don't have to, none of these cities will help, right, because A to C is solved, right. But okay, so we'll go to E, to Ergli, right, and so we add E, right, so these are 3 out of 2. Q only has B and D still, right, and now we're going to update. So we do this, 5 plus 9, is that how much, 14? Is that an improvement? No. Anything else? That's it. We don't have to do anything else, right? No improvement, we stay, right? It's pretty easy, right? Pretty easy. Like I said, he did it on a napkin. So of course now we have a 7-11, right? 7-11, right? And we pick, of course, we pick 7, right. So we pick 7. And again, it might look like, okay, it's almost solved, but not quite, right? Not quite. But at this moment, B is also solved. So in this moment, right, B is solved, right? And we have D, but we have not done finish yet, because what's happened here? You see, A, C, 4, we have to look at the neighbors, right, of B. We have B, C back. That's, in this case, again, if this luckily is not negative, so it breaks the algorithm, right? It's positive, it's not going to help, right? Because we came from C, we don't explore it. But we have D, so A, C, B, D is how much? 3, 4, 2 is 9. So what do we do? What should we be doing? Here. We should be A, C, B, D, right? We have current A, C, D, right? That's 11. But we have A, C, B, D, that is 9. So we have to update. Yeah, so we update this, right? So, of course, here it's kind of silly, right? Because we only have one vertex left. It's like, you know, we have basically solved the problem at this moment, actually, right? And, but yeah, we have formally, yeah, we check which one is out of one, you know, one vertex, which one is shortest cost, right? You know, D, and then we can close the algorithm, right? And that's done. We are done. We solved the problem. So pretty neat. But of course, this wouldn't be a computer science, right? If you didn't look at the complexity, right? Of course, Dijkstra was heavy on complexity, right? So we need to, let's see what's the complexity of this solution. And this is going to be dependent on how we store the vertices, right? We could store them in an array, right? If you store these vertices in an array, right? You know, or a list, or you know, something like that. Well, each time the excess, right, it comes out to be vertex time quadratic, right? But plus E, which is a number of edges, right? And the question now, how many, okay, you'll see this in graph theory. So what's the most edges you will have in this type of graph? You know, 5 vertices, right? Okay, if this is undirected, right, and not duplicates allowed, so how many could we have? So A, we have 4 connections, right? Let's say everything's connected, right? Like super connected, everything, right? We call this full, I guess, not fully connected graph, but full. Let me see what's called. Full graph, right? But now, yeah, on the, so it'll be 4, right? Then B is already connected to A, it'll be 3, 4, 3, 2, 1, right? 4, 3, 2, 1, that's what 10, right? But this is actually in general terms, it is, how do you calculate this, right? Well, let me add this. So on full undirected graph, right, would be what? Number of vertices, right, would be E equals what? Number of, you know, N times n minus 1 divided by 2, right? And n, where n is actually v, right? Number of vertices, right? Number of vertices, right? Right. So, does this formula make sense, right? And you've seen this before, right? Arithmetic progression, right? Right. So, now how about directed graph? What's the maximum there? Well, what should we do for a directed graph? What's the maximum there? From this formula or from here you can figure out. Each, right? It's even easier, right? Every vertex, right, has, well, you have connections to all the other vertices, basically, right? So number of vertices, right? So basically 5 times 5 minus 1, right? Because you don't need this 2 anymore, right? So I'll move this around, right? So for directed full edge count would be again E equals n times n minus 1, right? And that's it, right? And of course it makes sense, right? You just multiply by 2, right? You need this, you get rid of this 2, right? Because you always have doubles, right? On all both directions, right? So here we have, how many vertices do we have here? Well, sorry, vertices we have 5, but edges 1, 2, 3, 4, 5, 6, 7, 8, right? 8? No. Yeah, 8. So what's the maximum we could have here? We have 5 times 4, 20, right? So 8, is that a lot, or is that, how should I say? There's a term called sparse graph, the one which does not have many vertices, right? Well, it's I would say middle of the road, 8, right? It's not completely sparse, but it's also not completely full, obviously, right? So it's kind of actually, there's no full, strong definition what's a sparse graph, actually, right? But middle, you know, we have about half full, roughly, right? Meaning not every city is connected, right? Not in both ways. So, but these formulas make sense, I hope, right? So, going back to this, right? So, what does this mean to us, right? That this part E, right, is basically also quadratic, right? So why am I talking about this? Because notice part here, right? So this key point, sparse graph, right? So if this E is not too large, meaning it's not full, then we can actually make an improvement to our algorithm, use a different data structure to store our graph, right? Then we have this running time, E plus V, again that's length, right? This is length, how many, right? How many times log of V actually turns out. So but again, this is only good if E is not too big, right? Meaning it's not actually quadratic. Otherwise, of course, you're not going to make any improvement, because if this is completely full graph, right, that's going to be quadratic too, right? Because remember from our quadratic, from our discussion, this, right, or this here, right, it's quadratic, right? If you have to do something on the edges, you know, once, right? So n to the square minus n, right? Right? Yeah, so here again, a second. Yeah, equals n squared, right, minus n, right? This is still quadratic, right? Worst case scenario, right? Because this part here, remember from our complexity analysis, does not matter, right? As far as complexity goes, right? But this part here is more important, this is more dominant, basically, right? So, again, even if you had 200 here or 2000, right, it would be still quadratic, right? It's going to be very, very fast for small values of n, right? But again, for large n, it would be, you know, it would be still be quadratic. So, yeah, so that is important. So, let's look at this before the break. Let's look at why it works. So, there's a formal proof. Of course, Dijkstra proved it, but you don't have to, right? So, idea is this. Basic idea, right? A triangle equality, right? Basically, if there's UV, right? It's the shortest path between U and V, right? Then we are guaranteed that any other path we find, right, by definition, x between some other x, right, it's gonna be, at least equal, probably longer, right? You're not gonna make an improvement, right? So subpath, so that's why this is why the greedy algorithm works. Because subpath of any shortest path itself is the shortest path. So if you're going from Riga to Liepāja, right, you have to go through Skrunda, I guess, right? That's shortest path. I assume, I don't know, right? Assume or Saldus, right? But so shortest path to Saldus, right, will be necessarily part of the shortest path through Liepāja, basically, right? So if your shortest path goes through, right, it also could be the shortest path. Because why? Because if it's not the shortest path, you could make it to be long. You could find an improvement, and therefore you could also improve the bigger problem, right? So that's a whole trick, right? Each time you put a new vertex in S, right, of visited vertices, right, we know the shortest path to it, right? So it calculates the shortest path to every vertex. It's so we could actually use it from every vertex, right? Yeah. So basically use for some specific, right? Specific source to specific to many destinations, right? So usage, again, we mentioned this, routing, Google Maps, MapQuest, and so on. Routers, of course, again, mapping, so on, and also, of course, in epidemiology, right? How viruses spread, of course, as well, right? What's happening, right, for networks, right? So network analysis in general is a big field of topic of exploration, right? So, and I have actually in our papers, I have the original paper, right? Or his original paper here, right? And I'll show it here if you want to. If you are really bored, you can read. It's not very long, Maybe like 2-3 pages. 2-3 pages. Yeah, there. I think it's still available. Let me see if it's still available. Let's see if the link is good. It used to be. It's Yale. Yale is Yale. Yeah, there it is. Right. So 3 pages. Right. All right. You could, in the 50s, you could become famous in computer science, with 2-3 page papers. Right. Not so anymore. Right. Very unlikely. I mean, it's possible still. Right. But not very unlikely. Right. So, yeah. So pretty easy to read actually. Right. On connection with graphs, right? So, okay, so let's take a break, and we'll continue at what 10 o'clock? Yeah, 10 o'clock, right? And we'll look at some practical actually solving this.